In step 1, we start by gathering building footprints from public sources like Microsoft Global Building Footprints or OpenStreetMap. Then we extract the base and top heights of each building, calculate its minimum bounding rectangle, and create a 5-meter safety buffer around it. This buffer keeps the drone at a safe distance from the building's facade. Next, we automatically interpolate a series of one-dimensional flight points along the buffer's perimeter, and then expand these points vertically in 3-meter increments to form an S-shaped path covering the entire building. Finally, we export these automatically generated flight points to a KML file, making it easy to visualize and plan flights in Google Earth or other compatible platforms. Once we have the trajectory, it can be directly imported into the drone system. As you can see in the video, our drone can complete the entire building scan without any manual control. With the pre-planned path, the drone autonomously follows the calculated flight points, ensuring a consistent and precise scan of the building's facade from start to finish. This streamlined process significantly reduces the need for human intervention and increases efficiency in large-scale building surveys. In step 2, after the UAV flight, 2 types of data are collected: image data and 3D point cloud data. The image data is processed using the YOLOV8 model for object detection, which generates labeled images. These labeled images are then analyzed to extract specific information related to windows and other building features. Meanwhile, the point cloud data is processed using the MVS building algorithm. This advanced processing pipeline helps reduce noise and enhances the reconstruction of flat and textured surfaces, resulting in a more realistic and functional 3D model. Ultimately, this process allows for the extraction of detailed floor plans, layer by layer, ensuring each level of the building is accurately captured. All the semantic and dimensional information extracted from both the image and point cloud data is then passed on to step 3 for further processing and BIM reconstruction. In step 3, we use the Dynamo platform to automate the conversion of data into a BIM model. This process starts with the results from step 2, which include essential information such as floor heights, floor shapes, and window placements. Once the data is imported into Dynamo, the platform automatically generates key BIM components. In Dynamo, we achieve the reconstruction of components such as levels, floors, walls, roofs, and windows. Users simply import the data and click Run. Dynamo handles the entire process, from creating geometries to placing elements in the model. Afterward, the model can be opened directly in Revit for further modifications or queries. This automation eliminates manual modeling, saving time and ensuring accuracy. By automating these tasks, we can quickly generate a complete BIM model from raw data, which can then be refined in Revit. This streamlined process reduces workload and minimizes human errors, allowing users to focus on analysis rather than repetitive modeling tasks.